All right, are we live? Let's see, are we here? Hello world. Is it working? Is this thing on? Is this thing on? Welcome, welcome. Hope everyone's doing all right. Is this thing going to tweet this out so that way anyone who's interested can watch? Okie doke. So, welcome and hello. We're gonna do one problem quickly, then go get dinner, come back, probably do one or two problems, and then go to bed. So kth smallest element in a BST, given a binary search tree, write a function kth smallest to find the kth smallest element in it. So this is interesting. I don't know the answer to this. So an in-order traversal would give you the elements in sorted in order, right? Like it's as you might expect. So actually what you're going to want to do is perform an in-order traversal to the depth of k. And you can do this iteratively too. What if the BST is modified often and you need to find the kth smallest frequently? How would you optimize the routine? I mean, I'd still do the same thing. Probably, because you could do it's logarithmic time. K is always valid. It's 1,000 elements. Excuse me. Yeah, oh, my shoulder. Oh, definitely banged up my shoulder. I looked that up earlier the other day about basically what a chiropractor does. And yeah, I definitely damaged the tissue, and now there's scar tissue forming. Or it already formed and it's, healed poorly. I think that's more likely. It may have healed poorly, but it definitely damaged my shoulder. My other shoulder's kind of not doing too great either. It's got some minor discomfort as well. But my right shoulder is so much worse. My left shoulder's not great, but my right shoulder's... Actually, my left shoulder's pretty good. It's, for the most part, pretty comfortable. It's a little achy, but my right shoulder's it's killing me. I want to say we can just do an in-order traversal where you decrement k at each point, and k is sort of like a global variable. And when k is 0, I mean, decrement k, and when k is 0, then you return no, you need to do two things actually. You need to set whatever node that you're at, where you're looking at k, set that to what you're going to save, what you're going to return in your routine, and you also need to make this stopping point idempotent, because you have other routines now that are sort of queued up now. Excuse me. In the stack, you're going to pop all these other calls in the stack, and they're all going to update with their own point, their own node that it's at. So like for k is 3, you would start here, and then you would say, okay, decrement k when you look to the left. Look to the left again to decrement k. So it would be 3. So it's 2 here. It's 1 here, and is that right? In-order traversal. Excuse me, I think actually in the middle of with an in-order traversal, actually you gotta put it in the middle, not at the top. So you could put at the top, if k is less than or equal to 0, just return, just kind of terminate early. But you'd have a left call, which so you operate on the left subtree where k is 3. Then you operate on that left subtree where k is 3. Operate on that left subtree where k is 3. And then that left subtree where k is 3 is null. So then you return, set k to negative minus subtract 1 from k, because you process this node 1, and then you'd operate on the right subtree where k is 2, and then you'd go back to the queued up call, right? You'd have finished the left subtree now. Process k is now decrement to 1, and you have 2 here because you process 2. Take the right subtree, which is empty, which with k is 1, and then finally you would have your process here, and you finish this left subtree process here. K is now 0. You save 3. Process the right subtree where k is 0, which gives you that terminates early, right? That doesn't do anything; it just immediately terminates, as if it were a null pointer, null leaf. And then you would process this. Now, what's interesting is, right, so k would be 0 here. This is where you would want to use that idempotent value. And even though k is less than or equal to 0, you're not going to update your value again to write it again as 5. You're going to just keep it as 3 and skip this part. And then when you process the right subtree again, yeah. So you do need an idempotent element, a piece to it. But yeah, this is a pretty interesting question. I like this. I think even if you had a lot of deletions and insertions, it would still be. It's not logarithmic time. It's O of k time. I'm not sure how you could do this in logarithmic time. Like, I don't know if you could really do this faster than O of k time, right? I don't really know. Maybe I'm wrong. Maybe there is a way. There is a way to do this in logarithmic time that's even better than linear time. Like linear with respect to k. Is there a faster way to do this? I'll have to look at the discussion, because I'm thinking basically a binary search for the kth element actually is probably what you want to do, which would be logarithmic with respect to n rather than linear with respect to n. That's an interesting way to do it too. So let's try this one first, because these will both be, I think, fast enough, right? Linear with 10,000 elements should be fast enough, but logarithmic is even better. So I'll just find kth smallest, and we'll have this subroutine. It's going to be recursive. And we want root, or no, we have root, tree node root. We're going to take k, int, we'll say, we'll let it be n, let that be n. And we want to say if, so base cases. Yep. They want the number, right? The element, yeah, okay, sure. So there's always going to be one element in there, okay. So we can assume just return 0, I guess. And then it'll be sort of temporarily. Okay, so you say if not root or n is less than or equal to 0. And you're going to say f of root left, f of root right, f, and then now you have an idempotent, call it idempotent gate, false, and we'll say if n is less than or equal to 0, then ret equals root value and idempotent gate equals true. Right, so it's initially false, and while this is not false, you can update. Once this is no longer, once you've updated though, this is no longer false anymore, and you won't update again for the rest of the duration. And what you're going to do is decrement n here. Something like this. Oh, I have to call it though. Ret specified. I have to actually call this function, which is find kth smallest on root with itself. Okay, looks like it's correct. So we can do man, I've been listening to this song. It's so good. It's like stuck in my head. I don't know the lyrics though. I wish I could sing it. I wish I could just play it. It's Thrice Hurricane. Hurricane. It's a good one. It's a good one. Thrice Hurricane. The chorus is pretty good. It's gonna rain till the levee embrace. A tidal wave of fear and pain carries us away. Another fight into the night till nothing else remains. How do we find armor from the hurricane? Sheltered in the sands, shadows, the quiet song of your breath stirs the dark. Your skin like a rose neath my hand. And I can't keep from wondering why nothing good could ever stay. My faith feels like a fistful of sand. Yeah, this really speaks to me, this song. It's a good one. It's a good one. Okay, so let's get some other test cases here. 2 test cases. I think this is correct. I kind of just want to go for it. I think I got the edge cases. Well, go for it. Got them. Nice. Okay. So now the question is, all right, done, great, wonderful. Now the question is, how do we do this with logarithmic time rather than using an inorder traversal? Right. I think there is a way to do this in logarithmic time. You know why it can't be logarithmic time? It's a binary search tree, not a balanced binary search tree. So it doesn't matter. So this is it. That's it. That's all you got. And even if you're modifying the tree, it's still the same algorithm I'd run. Either way, insertions and deletions, still O of k time. Maybe you could do this. This would be kind of challenging to. No, you still. Yeah, this is probably. Yeah, I'd probably do it this way still. I was thinking you could do this using. You could do this with a threading and a what's that called? What's the algorithm called? The Morse traversal, I think it's called. The Morse traversal to do linear, iterative inorder traversal of the tree. However, that might not take O of k time. That might take O of n time every time because you have to thread the tree first. So I'm not sure about that. I don't know if that's worthwhile. I probably just use the extra memory for this, unless I really didn't want to use the extra memory, because you got to use some memory first for the stack, whereas the inorder traversal with Morse traversal doesn't use the memory for the stack. It uses the memory already present in the leaves that are empty. All right, that's it. Nice, well done. Let me see what other people have to say. Let's see. Recursion in order. No need to maintain list or stack. Really? Keep count resistance variable, avoid maintain list or stack. Fill. No, there's still a list. There's still a stack because come on, man. Give me that. The stack is the stack is oh, you know what you gotta do? You gotta order these by most votes. The stack is what do they call that? 4 lines in C++. Nice. He did such a good job, Mr. Pachman. The stack is the call stack. You have extra memory from the call stack. Now this is interesting. X is the left side. So what did he do here? This is so funky. All right, so K is the return value. Or no, K is, yeah, it makes it a reference, okay. So you basically pass it through every time, so it doesn't, yeah. If not K, so if K is 0, then you return X, and X is value on the left side. Otherwise, you're going to decrement K and say if not that, if you decrement it at 0, then you get the root value. Otherwise, even further still, iterate on the right side. So this portion is when I think you're on the right side, right? Basically, you call this. This actually probably should never happen if it's 0. I think the only time. I think only if. I think K is always. I don't think you ever call this. I don't think that ever happens. I think he can do this without X. Hold on. Let me see. Oops. Oh. Breadth first search. Depth first search. Recursive in order traversal. Iterative in order. Yeah, but it's still using a stack. I mean, it's always, anyway, let me see. I'm gonna just comment mine out for the time being and put it back when I'm done. Spend a little extra time tinkering. Oh, wait. What is wrong here? Wait, what? Doesn't return a value in all control paths. Oh. 1, 2, 3. What does he return? No. What? Let's go for it. It's fast too. All right. I don't think you need this. It's pretty good. I like this a lot. Just a really fancy way of doing the Inorder Traversal. Oops, I did it wrong. Meant to do this. Yeah, I meant to just comment what he has and modify it slightly. Oh, you do. Why is that? Really? It's a very interesting implementation. The left side, so you're gonna, whatever you return from the left side, iterate. Oh, excuse me. Okay. I got it now. Right, my mistake. Yeah, no, you need this. Because you've got to pass the value back up through the stack. So he's not using this, he's not doing what the funky thing that I do where you have sort of like a global local variable that's like sort of a static variable that's so as far as the function is concerned, it can kind of keep it can sort of keep mutating that address. It's almost like if you passed a reference or a pointer around. He's actually returning this x. He's returning once you've returned a root value, not like iterating anymore. Now you have sort of a call stack that you have to return the value that to return that root value has to be returned as a certain value. So that's where x gets stored and saved, is at each point step in between. That's pretty interesting. I wouldn't have thought about doing it that way. Wouldn't have thought to do it that way. And then so when you say the right side, same thing. You have take the left subtree as a value. We iterate on the left subtree, and whatever you get returned from the left subtree, you're going to return that value, or right, if this is the node you're supposed to process, or you're going to, no, it's the other way around. So this only happens, this always happens before this does. So you're always going to be iterating the left subtree, and then checking to see if if you should process that node and decrementing k, and if not, iterating on the right subtree. And sort of at every node you're going to decrement k. You're never going to hit this not k until this hits 0, and then that node that you're on, you're going to return that root value. And then all of the since the return value is either going to be x, the left side, right, the left subtree, or if this value, this recursion on the right side, this also returns a value. So yeah, you're going to end up cascading, either you're cascading back up this root value that you returned through the right subtrees that you iterated on, or through the left subtrees in this, if this conditional, through saving it first. You could go even further. No, so you need to process the left subtree before you check k. So this part of the code needs to be between the left subtree and the right subtree execution. I was going to say, well, why can't you just put this right here, right? Well, because this whole conditional really has to be between, all this stuff has to be between the left subtree and the right subtree, because this is still an in-order traversal. It's just, and then the processing is in the middle. This is really clever. I really like this a lot. I like that approach. I think what I wrote is a little more clear, but you can get from this to that without too much thinking. Although you do need, I mean, it's pretty clever what he did. It's pretty clever. I think this is a little more clear what's going on, why it works. But yeah, I like his approach a lot. Super, what do they call that? Super clever, super succinct. But not really like, I don't know, I wouldn't put that in production code, I think, because it would just be very hard to read in terms of like trying to understand what you're looking at, what it's doing. So it doesn't really, well, yeah, it could take a while. It take a while to figure out what's going on there, why it works, what it's doing. It's pretty interesting though. It's pretty neat. All right, let me go. Thanks for watching. Talk to you soon. Don't forget to like and subscribe if you like the stream. I'm gonna end stream here. So this is like super condensed video, rather condensed video, and then go get food, come back, hang out, eat, probably listen to the Bible, listen to an audio of scripture, and then yeah, we'll do like try to do a few more problems. Try to do like at least one before bed. I might do more than one problem if I have time. If it's like quick like this one, then I'll do that. But otherwise, I think I'll probably we'll just come back and do as many as we can. All right. So, thank you.